All right, good afternoon. Happy Thursday. How's everybody doing? Are you alive? The rain's got you down?
Yeah, it's crazy how all of our class had cloudy rain, so it'll make it today.
Yeah, I think that's it. That's what happened. Yeah, where is everybody? All those people that decide to show up for the test and then go away. What is that about? So tell me this first, a little feedback. The test on Tuesday, how you feel?
Fair.
You feel fair, or you feel the test was fair? Okay, good. You want to do the vote again? Okay, so thumbs up for it was the best experience ever. Thumbs down, it was the worst, and you can vote anywhere in between. Let me take a quick glance around. I see a lot of sideways. Kind of medium. It looks like nobody's terribly full of hatred at the moment for what happened, so maybe it'll work out. Okay. So need a little more time on grading that. Hopefully I can give them back to you on Tuesday. Make it Thursday. Just burn them, throw them away, whatever I need to do. Okay. So hopefully over the weekend at some point you'll get an email saying the grades are posted if everything goes well. Okay. So hate to ruin your weekend in that way. Okay. Well, you don't have to look. Just because I post the grades doesn't mean you have to look. So a couple of different things. First of all, as you know, the lectures are recorded so that you can watch them later. However, this one may take a little while to be posted, so I want to warn you in advance because earlier today I posted a video from another class, and YouTube took it down for no good reason. I think I got flagged by the automated system for some reason. So I appealed. It'll probably take a few days, so I'm guessing they're probably not going to let me upload anything else for a few days. So we'll see what happens with that. It'll be there eventually. So today we are going to pick up where we left off a very, very long time ago at this point. I think it's been about 3 weeks since we actually had new material. I don't know, something like that. It seems like it's been forever. And we're back in the chapter on magnetic field. We had just introduced the ideas of magnetic field and kind of what was going on there a little bit, but we didn't get a chance to really dig into the depths at all. I just introduced things. So we're going to start on this slide that's labeled the magnetic force, and we're specifically going to talk today for most of the time about how magnetic fields affect the motion of charges, okay, in different configurations and things. And that's most of what this chapter is about. In the next chapter, we're going to flip it around the other way, and we're going to say, like, how do charges that are moving in different configurations actually produce magnetic fields. So at this point, we're just going to assume that something is making a magnetic field, and we're not going to worry about what's doing it. Just keep in mind that's coming in the next chapter, all right? Now, as I look through the material that we have yet to cover, there are a lot of things that I need to get to in the 5 lectures we have left, which is almost nothing, I know. So there are going to be things in the chapter that I have slides for that I'm just like, I need to hit the high points that will just kind of slide, like literally slide right on by, okay? So there's just things we need to definitely cover and some things that are a little less important, and I'll be jumping over some things that I deem a little less important, all right? So first of all, let's talk about the magnetic force. This is specifically the magnetic force on a moving point charge. The magnetic force on a moving point charge. The word moving there being a little bit weird. If the point charge isn't moving, if it's just sitting in a magnetic field, it experiences nothing. It doesn't feel a force from that magnetic field. Nothing's happening. This is the way that I kind of like to think about it. Let's imagine, how old are you people? First of all, how many of you are over 21? Okay, I'm going to go with the example anyway. Just you'll get the idea. Okay, so let's imagine that you had an awful good time last night, right? And you wake up this morning feeling a little bit woozy. Okay, and you're in your bed. You sit up. You're like, I can do this. I can walk to the bathroom. Right? I feel great. Everything is fantastic. I don't have any problems at all. You're like, this is fine. And then you take a step, okay? And you think you're going to just go straight, like everything is fine, right? But you take a step, and immediately it's like, whoo, I feel a force this way for some unknown reason. you are a point charge in a magnetic field. If you're just there, in this case, the magnetic field is all the illness that's coming from something, okay, that's making you a little woozy. As long as you're sitting still, things are good. You don't feel any sideways forces or anything. If you start to move, you experience a force from that thing that's impacting you, okay? You have to have a moving charge in order for it to experience a magnetic force. So let's talk equations a little bit. First of all, we'll write this as F sub B. Remember, B is the magnetic field. So this is the force from the magnetic field, and it is equal to Q, the charge that's on our point charge, times the cross product of the velocity of that charge and the magnetic field. Cross product, yay. We have to go back in time and maybe refresh our memories on that just a little bit, okay? QV cross B. So clearly there's a V in there. If V is 0, there's no force, okay? So the equation tells us that's true. Don't forget, if I want to just look at the magnitude of a cross product, it is Q times the magnitude of all these, Q, V, B, sine theta. And remember that theta is the angle between those two vectors, between the V vector and the B vector. We'll talk about direction on the next slide, which is where we all get to have some fun, okay? The magnitude of this force is the charge times the velocity times the magnetic field times the sine of the angle between those two things. Let me put a little caveat here at the bottom. Let's see. Actually, let's do that on the next slide. Let me get rid of that. Okay. If we want to talk about direction, we have to use the right-hand rule, which I think we did a little bit earlier, and if not this semester, certainly you did some in 220, okay? So maybe this is a refresher in some cases. So the right-hand rule gives the direction of this force, and we are all going to do this together. And specifically, it gives the direction on a positive charge. So the best way to illustrate this is with these weird halfway invisible ghost hands that are kind of there. You can kind of see them a little bit, right? I think they're there, okay? And instead of actually writing a bunch of notes about these fingers have to do this and those fingers have to do that, let's just step through it all together, okay? So let's pretend that there is this positive charge and it is traveling off in this direction, directly to the right, okay? In that same plane, but kind of over to the side, back behind that velocity vector is the magnetic field. So maybe if it helps, imagine you're the charge that's going this way, and the whole time there's a magnetic field that's kind of pointing right over there. Okay, everybody got that? You can see that up here, right? Take the fingers of your right hand. Everybody with me on this? It's almost like we're going to do a group dance or something, right? Fingers of the right hand in the direction of the first vector, which is V in the cross product, okay, the first one that's there. And then orient your hand in some way such that when your fingers naturally form a fist, they turn toward the direction of the second vector, which is B, okay? So if I'm going this way and B is pointing over there, clearly I need to orient my hand with my thumb up for my fingers to like turn over toward the direction of where B is pointing, okay? Unless you've got a weird hand and you can turn your hand like this and then make your fingers like, oh, like that's like maybe a little bit, but that's not the natural direction, right? So it turns like this. Notice which way my thumb points. The force here is up. So if I'm a charge that's positive going this way, in a magnetic field that's kind of pointing out to my left a little bit, as I try to move this way, I'm going to feel a force that makes me want to go up. Now, the next instant, all of a sudden, I've changed my direction a little bit. Everything is different. We have to reevaluate because now my velocity is in a new direction, and I have to evaluate where the force is going to be next time, okay? If this is a negative charge, you can do the exact same thing, just when you're done, be like, ooh, my thumb pointed up. Ooh, it's negative. Let's just flip it the opposite direction, okay? Or I guess you could use your left hand, but let's not go there, okay? Right hand only. You remember how to do this. You feel okay with that? as we go through today's lecture, we're going to be doing this a lot, okay, with a lot of different examples and multiple choice questions and all sorts of things. So I hope everyone will play along maybe a little bit. It tends to get quite a bit confusing if you're not on top of what this is doing. So let's start with this. There is a positive charge, it says, that's moving up in the plane of the screen. And all of these little X's indicate that there's a magnetic field that points directly into the screen. So let me write that here. Magnetic field into the screen. Figure it out. Which direction is the magnetic force on that charge? Yes, all of you should be like grabbing at flies right now, looking kind of weird. I like that intermediate look that so many of you get on your face. You're like, I've got this, like V, and then all of a sudden it's like, and you just kind of drift into this place where your hand's just sort of floating in the air. All right, let's do this one together. V is pointing straight up, so my fingers go this way. And after you do this a little bit, you start to automatically put your hand in the direction that it needs to be. B is pointing into the screen, so I need my fingers to be able to bend that direction. Okay, so my hand doesn't want to be like this unless my fingers break. Okay, which way is my thumb going to point? Looks a whole lot like to the left. Okay, so how many of you got that right? How many of you are lying? It's hard to say, huh? So to the left. Let's try another one. Positive charge still. Moving to the right, magnetic field is into the screen. You two over here look like you're going to hurt your elbow. I keep seeing this like. Mind the way. No. Velocity's this way. I need my fingers to turn into the screen like that, right? It looks like my thumb is pointing up. So in that particular case, we've got a force that's up. How about one more before we do a rather involved example problem? Now the magnetic field is just pointing to the right, and it's in the plane of the screen. And I can't tell if you have questions or not. There's just a lot of this. You know, what does that mean? Some of you are unsure which way your fingers turn. Yeah. It's like velocity's up, but I need my fingers to turn that way, right? Which means that my thumb is going to point into the screen. Did you catch that? You look a little uncertain about that one. V is up, B is over to the side, and look, all of a sudden I'm making weird, like, shadow puppets or something. And then into the screen, or into the page as they've written it here for the direction of the magnetic force. Okay? Any questions before we deal with this example that's in terribly small print? Anybody? Okay. Prepare yourself for this. This one tends to be a little confusing, okay? But there's going to be a lot of right-hand rule and stuff in here as we try to sort it out. First of all, it says there's a bunch of particles, they're traveling in a magnetic field, and the magnetic field has unknown magnitude and direction. So you might immediately get the idea, I bet we're going to try to find which direction and magnitude the magnetic field has. That's our goal. We make a couple of observations. First of all, there is a proton positive charge moving at 1.3 kilometers per second in the positive z direction, and it feels that force in the positive y direction. Ugh, we're going to need a diagram really quick. Let me just point out that they're also going to say that we observe an electron, negative charge, that's moving in a different direction and feels a force in another direction. We're going to try to use these two observations to try to figure out what's happening with the magnetic field, okay? So let me start with a couple of diagrams that I think will help us. Let's start over here with the proton. And I'm just going to draw an XY plane. And it says that we observe the proton moving in the positive X direction. So let's go ahead and draw that on here. We've got a proton. It's moving in the positive X direction. So that's the direction of its velocity. Okay? We're given a value for that velocity up there somewhere. Yes. Okay? And it says that it experiences a force in the positive Y direction. So we could say that there's a force on the proton from the electric field that points that way. And I'm going to put sub P. We know it's coming from the magnetic field, but I'm going to denote that we're talking about the proton in that particular case. Roughly speaking, what can you tell me about where the magnetic field might be pointing? You are not at this point able to give me an exact direction, but you can give me a range of directions. It's kind of working backwards, right? So I might as well point my thumb in the direction of the force and kind of work from there. Notice the velocity is to the right. My fingers want to curl sort of behind the x-axis somewhere, right? Now keep in mind, it's not necessarily perpendicular straight back, it's just behind it somewhere. So if this is the x-axis this way, it means that over that direction somewhere is where the magnetic field is pointing. I don't know exactly where, I just know it's over there somewhere. So somewhere like in this quadrant between positive x and negative z. Do you see that? A lot of three-dimensional, like moving things around, okay? So just imagine that somewhere like behind this axis back into the screen at some angle is the direction of the magnetic field. We could draw that. Let's say, first of all, B is, I don't know how to write this, we'll say behind the positive x-axis. And if I were to flip this coordinate system around and say, draw something like this, maybe this is positive x, and this is positive z, what we're saying is that the magnetic field is back here somewhere at some unknown angle. We'll call that angle theta. Ooh. Are you okay so far? The other data point from the electron is going to help us like narrow down exactly where in this quadrant it's located, okay? So let's see if we can figure out anything about the magnitude just from this point. So let's see, the force on the proton is Q V B sine theta. They gave me the force. We know it's a proton, so we know the charge. They gave me the velocity. I don't know B or theta. Well, that's a little bit of a problem. But here's what I can do. I could just solve this for B sine theta, and let's see what we get. So that's going to be FP over QV. Let's plug those numbers in. Someone help me out with the calculation. That's 2.1 times 10 to the minus 16. And in the denominator, we should have 1.6 times 10 to the minus 19. And the velocity, be careful, notice that's in kilometers per second. I want that in meters per second. So that should be 1,300. What do you get for B sine theta? Go, fast. Who's got it? Anybody? You're not that fast? Be faster. 1.01? Yeah. Okay, that works for me. 1.01, and that's going to be in units of Tesla. Okay? Take a look at this diagram. B sine theta. What did we just find? Any thoughts? I'm just pointing random places, apparently. we essentially just found this, right? You okay with that? Vector components, all of that type of stuff. We just found the negative z component of my b vector. Okay, so if I found one of the components, I just need to find one more, and I can put everything together and figure out what direction and magnitude it is. So we just found b sine theta, which is one of those components. Let's see what the electron tells us. And this is where the confusion gets to happen. Let's do the same thing and keep this coordinate system identical, even though they gave us some different directions. Otherwise, I think it just gets extra confusing. So this is plus y, and over here is plus x. And we're dealing with an electron this time. Oh, I should be consistent with the colors, shouldn't I? Yeah, I guess so. So we've got an electron there. And let's see what it says. It says the electron is moving in the, whatever that is, negative z direction. Okay, well, I can't really draw that terribly easily, so here's the way I'm going to do this. We'll say into the screen is the direction of the velocity vector. Okay, so pointing away from you is the direction of the velocity. And it says that it experiences a force in the positive y direction. That I can draw. So let's see, force this way on an electron. So V is pointing directly away from you. The force on an electron is up. Keep in mind, for the right-hand rule, we deal with positive charges. For it to work, the thumb gives us the direction of the force on a positive charge. So let's just go ahead and draw in here that this opposite direction would be the direction of the force if it had been a proton. Okay? Now, based on that, again, where is the magnetic field? You should get something that agrees with the first part, otherwise all is lost. Wow, the sun is nice. It was terribly wet and disgusting earlier. Just a second ago, huh? Wow.
For like the
It is quite wet.
Yeah, but it was also raining just like while it was sunny.
Yeah.
Yeah.
Should be a rainbow out there somewhere. Go find it.
Oh,
Yeah, I thought so, yeah. So let's see, once again, force on a proton. My thumb is pointing down, right? Or this way, perhaps, I don't know. So what does that tell me? The velocity is this way. Everybody still with me there? Thumb's pointing down, velocity's into the screen, which means that over there somewhere has to be, I like all of us are just doing this now. It's like, hello. Over there somewhere, again, behind the net positive x-axis is where the magnetic field is located. But notice, this time we're coming at this from a slightly different direction. The last time we were measuring it from positive x going back behind it. This time I'm measuring from negative z bending toward positive x. In other words, this is helping me find this angle, the opposite angle or the complementary angle, which is really going to help narrow this down. So if we wanted to, let's say that this is phi, we could say that the force here is going to be Q V B sine phi. And I can find B sine phi, which is F over Q V. And when I find that, I'm finding another component to my vector. So that is this one, B sine phi, which now I have a vertical and horizontal component in the x and z direction, which means I can find the magnetic field, okay? So I will let you plug those numbers in. Since I gave you the one example of the calculation over there, you should be in pretty good shape. This time you should get 1.13 Tesla. And now, since these are my two components of the B vector, well, that's just a Pythagorean theorem away from finding B. So the magnitude of the B vector is going to be the square root of 1.01 squared plus 1.13 squared. And for that, I've got 1.51 Tesla. And then we could solve for either theta or phi. Either one would give me exactly what the direction is. I just have to be a little bit precise. Let's say that we try to find theta. That'll be the inverse tangent of 1.01 over 1.13, which is 41.7 degrees. And I'll write that as under the positive x-axis toward the negative z-axis. Maybe that's a little extra precise, but that should tell you exactly where it is. Right-hand rules, calculations of magnitudes, finding whatever the unknowns are. Who's got questions, complaints, thoughts, anything? Nothing? You're happy? You've got it all figured out? You know all the answers? Okay. Yeah, I didn't think so. All right. Now, let's compare this to what we learned about electric fields. Remember, with an electric field, if I have a positive charge, it feels a force in the direction of the electric field. So imagine we have a positive charge that's trying to move to the right, and it's in an electric field that's pointing straight down. Well, this is not terribly unlike, I don't know, if I just try to toss this iPad across the room and it feels a gravitational field straight down, it's going to get pulled in that direction. And we drew a lot of analogies with like the electric force and the electric field and gravitation, and the equations even looked exactly the same because that's really how it behaves, okay? But the magnetic field is really, really different. In fact, we had to use the right-hand rule. We didn't have to do that with the electric field and the electric force. It was just like, oh, it gets pushed in the direction of the electric field. End of story, okay? Notice what happens if I set it up exactly the same way. Again, I'm going to have a positive charge that's trying to go to the right and a magnetic field that's pointing straight down. So this is the exact same situation. I've just switched the type of field. Look at which direction it gets turned this time. And we can figure this out ourselves. Velocity is this way, and magnetic field is down. So when it's in this position, it gets turned that direction. So you can imagine it's trying to go this way. It's like, oh, I get bent this way. Again, the magnetic field is pointing down, and I get turned off this direction, okay? Notice what happens, though. If I continue to go around that direction just a little bit, now my velocity, instead of being here, is maybe here, okay? It's just shifted a little. Velocity like this, magnetic field is still down. Still, I'm getting pulled off to the left. So it's like, oh, I got turned a little bit more. It doesn't really matter where I am. Again, it's like velocity this way, magnetic field is down, the force is to my left. I end up just like going in a little loop, right? This poor positive charge is stuck. The magnetic field is exerting a force, but it's always a force to its left. It's almost like there's something out there like holding its hand, spinning it in a circle. It's having all kinds of fun, right? It can't go anywhere. It doesn't get shifted out of the magnetic field. It just turns in a little loop, and that's it. So you can see that the forces from an electric field and a magnetic field treat charges drastically different. Okay, your question.
Is that how particle accelerators work?
Oh, magnetic fields are involved, but we don't just send them into like little tiny loops like this. Instead, we're talking massive loops. You're not going to get very far with just like one direction and then one magnetic field. A whole lot more is involved. Anybody else? It's getting dark now. A second ago, you were all in the bright sunshine back there, and now it's like an evil spirit has come over us or something, and life is terrible. Let's see. What was on this next slide? This one we're going to skip. Ooh, here comes some skipping. This is what we were just talking about, okay? So circular motion is what you get. Remember, all the way back to Physics 220, you learned about circular motion. You learned about, like, forces that point in a centripetal direction. Does any of that ring a bell at all? Does anybody remember centripetal acceleration? Does anybody remember the equation? Ooh, v squared over r. Wow, okay. Let's see where this gets us really quick here, all right? So this is what we had 2 slides ago, right? It's just now we're looking down on top of the circle, okay, and looking at that force that's always out to the side. And also it looks like it's going in the opposite direction this time, so you get the idea. Here we have a velocity that's out that way. Make sure that you agree with what you see here. So the velocity is this way, the magnetic field's pointing out, I get a force that's up. And that same thing happens no matter where I am on the circle, and here's a bend I can't make, right? Like that. And then once more, I need my hand to go down, and then my thumb goes to the left. You get the idea, okay? Everywhere in that circle, it always has a force off to the side, okay? So we can put a couple of things together. If we were to make the assumption that this is the only force that this charge feels, we could say that the magnetic force, which we know is QVB sine theta, and here the velocity and the magnetic field are 90 degrees apart, which means that's just going to be 1 because theta is 90. And since it's the only force, I can set that equal to the mass times the acceleration in the c direction, if you want to think about it that way, or the centripetal acceleration. In other words, this is equal to mv squared over r. QVB is equal to mv squared over r. And then we could rearrange a few things and solve for r. So let's see, r is going to be mv squared over QVB. And then one of my velocities gets canceled out, and I just have mv over qb. And this is the radius of the little loop, the little circular motion that's going to happen. And you're thinking like, well, that seems a little esoteric. Who cares? Why do I want to use that at all? I'm going to give you an example on the next slide, which you have in front of you, maybe, so you know what that is, okay? R is equal to mv over qb. Has anybody ever heard of a mass spectrometer, or maybe used one in a lab, or seen one on a TV show? I don't know, did anybody, you used to watch NCIS? No, nobody's yet. You've seen reruns, whatever. Like the person in the lab that did the forensics had a mass spec. It had a name. I don't even remember what the name was. I think it was Major Mass Spec or something. I don't know. Like she could whip up answers to everything in way less time than any of that would actually take, of course. Okay, mass spectrometer can use this behavior to do a couple of different things. So first of all, we could do something like this. We could separate isotopes. Isotopes, essentially just atoms of the same element, they just have a different mass, okay? And again, look at that equation we just had, R is equal to mv over qb. So if I can control the velocity of these particles, these isotopes, and I know that they all have the same charge, and I'm also able to control the magnetic field, I could set up a situation like this where I inject at a certain velocity these isotopes into a set magnetic field that's coming directly out at you. And depending on what the mass is, those with a larger mass are going to go in a larger radius circle. Which means what you could do is almost, and please don't take this literally, okay? Like set up little buckets over here, right, at different radii. And, you know, ones that have different masses will curve a different amount and go into the different buckets so that you can basically collect different isotopes at different masses. That's kind of cool, first of all. But what if it was something else? What if it was the other way around and perhaps we wanted to figure out what the mass was, right? Instead of trying to separate them, maybe I insert a bunch of particles all with the exact same mass, but the mass is unknown. If I can measure exactly what the radius of curvature is when it turns, well, then we can just flip that equation around and find the mass of an unknown charged particle, okay? So, I don't know. It seems kind of like random when we're talking about it over here. Then all of a sudden, people can build equipment and do some pretty cool stuff, okay? So, we're really not going to do this. We could make it more complex, but there's no need to. This one is a trick question, so I'm going to skip that. And then I'm going to let you try to figure this one out, which is just a little bit more practice with the right hand rule. feel like we should have some sort of right-hand rule-ish thing on every topic, because it seems to be like the most engaging thing we do all semester. It's like something that like involves a limb. Like all of a sudden you get to do things and you're like, oh, I can do this, you know, and then you get to play a little bit. I don't know. Maybe we should go back and be like, when solving this problem, you have to do 3 push-ups. No, no, that sounds terrible. So let's see, the velocity is to the right, and clearly it experiences a force up because it gets turned that direction. So which way is the magnetic field? It must be back that way somewhere. Okay, so into the page in some capacity, all right? And this one you should be able to figure out based on the equation we just talked about. R is equal to mv over qb. Same mass, same speed. Which one has the larger charge? Looking at this equation, larger charge is going to mean smaller radius of curvature, which means that 2 is going to be our answer there, okay? And finally, not finally, there's 2 more. This one I just want to tell you about, and then I'll let you do the next one yourself. Notice in this particular case, same sort of thing, proton, it's getting turned into a circle by a magnetic field, but it's asking about what happens to the kinetic energy of the proton. What happens to the kinetic energy? Remember that kinetic energy is equal to 1/2 mv squared. The velocity, the magnitude of the velocity would have to change for the kinetic energy to change. Keep in mind, when something is turning in a circle and feels an acceleration that's perpendicular to the direction it's trying to move, all that acceleration does is change the direction of the velocity. It doesn't influence its magnitude. So this charge that's getting turned in a circle, just going round and round and round, it's always going at the same magnitude of velocity. It just keeps changing direction, which means the kinetic energy never gets changed. In the case of an electric field, I have something that's like getting pulled and gets accelerated in a direction. In that particular case, it's putting energy in. It's making it go faster. The kinetic energy is being changed by an electric field. So a key difference between the 2 of those. So in this case, the kinetic energy is going to stay the same, okay? And then finally, I think this one is a kind of a 2-step problem that will test your skills at this point. I'll give you a second. Notice electrons. Also notice electric field. The answer is not number 5. That is never the answer on any of your test problems. I promise you. I give you problems that can be worked. It's not impossible to accomplish. Excuse me. Someone wants one. I'm just doing 2 things at the same time. There's multitasking here. You like that? It's pretty good. Anybody got this problem figured out yet? 3? 4? So let's talk first of all about what the electric field is going to do to these electrons. And we're going to try to counteract that with a magnetic field and a magnetic force. So electrons are not going to be drawn in the direction of the electric field. They're going to be drawn in the opposite direction, right? There's like double confusion here, which is terrible. So as these electrons go into this electric field, they're going to want to bend down this way, okay? Which means that protons would have want it to be turned that way. Everybody okay so far? Okay. So in other words, I would like to be able to use the right-hand rule. I just immediately like transferred everything over to protons just because that's how we think about all this stuff. I would like to counteract a force on protons that would be that direction, which means I want to create a magnetic field that gives me a force downward. Did you follow all those steps? Should I write that down? Should you write that down? I don't know. I'm going to write that down, okay? So these electrons will feel a force that way. Electrons feel force down, okay? Which means that protons would feel a force up. Say would. Okay? We want to counteract that force, okay? So we want to create FB that points down. And then it's possible we could counteract those forces and make them just go straight through without being deflected at all in either direction, okay? So if I want to create a magnetic force that's down, right? My thumb points that direction. V is this way. Which way are my fingers going to turn? Oh, it looks a whole lot like out of the page, okay? Question.
So how does a magnetic field affect different charges?
It's depending on positive or negative, the magnetic field can affect them both, just in the exact opposite direction. The right-hand rule will tell us what it does on the positive charge. The negative is just going to feel the opposite. Okay? So what did I just say the answer was?
4.
4. Okay, out of the page. Good. That was fun. Yes. All right. So let's see. I'm going to save that question in case we have a little time at the end of class, something for you people to do. It's not a terribly hard one, but we'll come back to that if we have time. All right? Let's take this a little bit further. All we've talked about so far is if I have a single individual charge traveling through a magnetic field, what it feels. We could ramp that up. What about current? Current is the same thing, just like a bunch of charges, right? So it makes sense that if I have a current that's flowing through a wire, and that wire is in a magnetic field, that entire physical thing, that wire, should feel a force. If the current's not flowing, it doesn't feel anything, okay? So it's, again, the same exact idea. We're just scaling it up because there's a bunch of charges moving. So let's start in this particular case with the equation, and then we'll talk about the cross product and the right-hand rule. So the magnetic force on a wire that has charges moving through it, current, is equal to the current times the length vector, which I'll explain in a second, crossed with the magnetic field vector. And this is a vector that is along the wire in the direction of the current. If you look at that equation and stare at it for a second, you will see that it's really no different than the other equation, right? We had a velocity before. We've just replaced that velocity with the current, which is both about the charges moving, right? We previously, what did we have? Q, V cross B. So here we have the direction that those are flowing, which was velocity before. Now it's a vector that points along the direction the charges are moving, and the magnetic field is still the magnetic field. So really this is the exact same equation, just scaled up to deal with a bunch of charges flowing in a wire instead of just one charge flowing through a wire. Let's see, a couple of different things. So this magnitude will be just what you would expect, ILB sine theta. And you will get the direction from the right-hand rule. And we get those lovely ghost hands again. Okay? So once again, start with your fingers in the direction of the first vector, which is the L vector, which simply points in the direction of the current. So the current's going this way, fingers go that way, okay? Orient your hand in such a way so that your fingers can naturally turn over to the second vector, which is the magnetic field. and your thumb points in the direction of the force on this wire. So you can imagine this wire, as current flows through it, feels a force directly out towards you at all points along the wire. So when you're building a circuit and it has to like go into a region with magnetic field, these are things people have to consider, right? You don't want to have problems where all of a sudden it's like, ooh, I turn on the current and the wires in my circuit go and get like yanked over somewhere else and potentially even broken, or maybe touching something that could rip them open, and all of a sudden you've got short circuits and everything is terrible, okay? Real mechanical, physical forces are felt by the wires in the circuit if they pass through a magnetic field. That sounds like a potential problem, okay? So really this works exactly like what we had a moment ago. So I will give you one of these and you should quickly get to the answer because this looks a whole lot like what we just had. They just shifted the magnetic field a little bit. Current's that way, magnetic field is up. Looks like my thumb points out of the page. And one more, just the one more. I love this one because it breaks your hands. Yeah, did you feel your hand get stuck that time? Right? Because you're like, okay, fingers in the direction of the current, I got that. And now I need to turn them in the direction of the magnetic field. I don't know where to go. It's already pointing that way. What do I do? Thoughts? Zero. Zero. It's not going to feel a force. Go back and look at the equation. There's no angle in between I or L and B. Sine of 0. We're done. There's nothing there. It's 0. So if we orient the current through the field in this direction, it doesn't feel a force. That might be one way to solve the problem of not having your circuit get broken by the magnetic force. Okay? Orient it so that the current goes in the same direction as the field. So there we have 0. Let's see. Now, if you look in front of you right now, you will see that there are a ton more slides that I put in this particular pre-lecture. It turns out that I put in a bunch of slides that pertain to the next chapter. So I've since made some changes and put them over into the other chapters. So this chapter is really close to ending, even if you think it's not. And then we're going to have a little bit of time to jump to the next chapter, perhaps, unless you'd rather work a problem. Maybe a little of both. We can do all. Why does it have to be or? Let's make it and. So in this particular case, due to the lack of time remaining in the semester, I'm going to qualitatively tell you what's happening here. We're not going to go through the derivation or work problems with it, okay? I want to point out that based on what we just talked about, the fact that wires in a magnetic field feel a force, if we make a loop of wire and put it in a magnetic field, something very interesting happens. We're not going to learn why this is interesting until a couple of chapters down the road, but I want you to keep this in the back of your mind. Here you go. Imagine what happens with this loop of wire with, say, current. Have they drawn the current? The current's going around this clockwise, okay? So let's start by looking at the left segment of wire and imagine the current is going up and the magnetic field is to the right. So this segment of wire is feeling a force away from us, okay? Look at the top and the bottom. For the top, the current's going in the same direction as the magnetic field. We know it doesn't feel a force. The bottom, the current's going in the opposite direction to the magnetic field. That's also going to give me 0. It doesn't feel a force, okay? What happens on the right side? On the right side, the current's going down, right? And the magnetic field is still over to the right. Notice there's a force towards you. So the left side of this is feeling a force into the screen, and the right side is feeling a force out of the screen, okay? That means that this loop of wire naturally wants to rotate in the magnetic field, okay? So instead, if I drop it in this configuration, it'll flip like this and probably overshoot a little bit and end up making itself sort of perpendicular to the field instead of parallel, all right? This is happening because we're getting torque. Ugh. Torque from 220. You loved torque, right? Just nod and say yes. You all loved torque. It was your favorite thing ever. Oh, I can't get you to do that. Do you have a question?
Is it acting like a magnet?
Is it? What's it?
The one.
Yeah, kind of. In the sense, if you're thinking like a magnet wants to orient itself in the field, it's a similar effect. Yeah, because we're going to see later on that actually it kind of is. Current creates its own magnetic field as well. So that's really kind of what's happening. Okay. So this diagram on the right is like looking at this from the top, and they're showing the forces, one into the screen and one out of the screen. It's just now we're looking top down instead of at the front. And you can see how it makes this thing want to rotate, assuming maybe I put it on some kind of an axis in the middle, all right? You can get clever with this. Now, instead of making it just go boom and like stop here, if there's a way for me to like make the current keep switching directions, ooh, I think we've talked about something along those lines before, okay? Then I could potentially make this thing keep spinning around and around and around and around. And all of a sudden, we've got an electric motor, which, ooh, yay. And then if I've got an electric motor, I can later build things like electric cars. Ooh, yay. So that's... I told you too much. The secrets are out. Elon Musk somewhere just said, shut him down. No more of that. All right, let's see if we can make a reconnection here. We can fix this. It can be fixed. Come back. That was pretty good, right? You like the timing? That wasn't too bad, all right? So we're going to talk about that in a little more detail later on, but it's kind of cool that something as simple as magnetic field and sending current through a wire can all of a sudden make the cars on a tire turn really, really fast and make a car go forward. And you got to get the idea that also that's a whole lot simpler than like a gas engine. Have you ever really thought about a gas engine? It feels like such a hack. It's like, let's make little tiny explosions that will make things like move linearly, and let's connect that to something so that when it moves linearly, it's connected to a wheel that like does this sort of thing. Like let's turn linear motion into circular motion, all because I have little explosions. Who wants to drive around like that, right? In my vehicle with little explosions. We've been doing this for, what, 100 years now?
Over.
Huh?
Over 100.
Over 100? When was the first car?
Very old, 18.
Was it 18? I was thinking early 19.
Oh.
I don't know history.
Mercedes is over 100 years old. Same with Ford.
I don't know. So we'll say 1XX years, something like that, of driving around with little tiny exploding interior vehicle things.
1885.
1885.
Told you.
Wow. It's pretty impressive for the time. But now looking back, it's like hack upon hack upon hack upon hack upon hack
We should have had
to make it better.
by now.
We could have what?
We should have floating cars by now.
Floating cars?
Yeah.